Let me talk about the assessing of the equivalence of fitting polynomials. This is something that is interesting because if we have an approximation problem, there is always the question of what should be the degree of the chosen polynomial. So should it be a straight line? So should be quadratic? Should be so what's the degree? How much can we go? So in other words, would a polynomial of degree d be equivalent to one of degree plus 1, therefore making no difference in trying another of higher order, higher or lower degree? Okay, now here they think of order and degree. They get confused, and myself sometimes change that. It is just a flaw in the how we say. The proper term should be degree. So we can do a statistical test using a Fisher distribution to test the equivalence of fitting polynomials. Okay, so which means that if two polynomials are statistically equivalent, it doesn't matter if to continue try to fit higher degrees. Sorry, here the problem I just mentioned, because it's they're equivalent. So consider two polynomials of degree d and d plus 1. The number of unknown coefficients in each case equals to degree plus 1. So let us call them, in this case, ud and ud plus 1. This is the number of unknown coefficients. If we consider n observations, the degrees of freedom will be respectively n of d, degree d is n minus u sub d, and the degrees of freedom of the polynomial of degree d plus 1 is going to be n, number of observations, minus u d plus 1. This is the number of unknown coefficients for the polynomial of degree d plus 1. The test is carried out using the quadratic form of the residuals. So Q is the quadratic form of the residuals. And here is the statistic. This is statistic y. So the statistic y is formed by the product, by the absolute value of the product of two ratios. The first ratio is the difference between the quadratic form of the residuals for the polynomial of degree d minus the same quantity for polynomial degree d plus 1 divided by the quadratic form of the polynomial degree d plus 1. The second term is computed as a function of the degrees of freedom. So the Fisher distribution, you know that it's a function of 2 degrees of freedom. So the first degree of freedom is basically the difference between the degrees of freedom, or between these two consecutive polynomials, and the second degree of freedom is the degree of freedom of the polynomial of large degree. The degrees of freedom of the polynomial with large degree. 1 minus alpha. Example number 1. A data set has n equals to 1 observations, and it was fit by polynomials of several degrees. Test if the fourth and fifth degree or degrees are equivalent. Confidence level 95%. We are given here the residual. Actually, we're being given here the quadratic form of the residuals. Okay, you'd have to compute the residuals for that. But anyway, the quadratic form of the residuals for the fourth degree is 678. For the fifth is 555. These are the number of unknowns. Here we are applying the test. This is the quantity y. So our y is 1.11. The value that we get from the Fisher distribution is equal to 6.6. So the test passes. The null hypothesis is accepted. What is the null hypothesis? That the polynomial of degree 4 is equivalent to polynomial of degree 5, which means we can basically just, if you're doing trying different polynomials, you can stop at fourth degree. Second example. Now, this is a little bit more involving because you are given the actual data sets. And I'm basically showing here how I did with the MATLAB. So given the time series, observations, 1, 2, blah, 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 and its associated time tags, tau, blah, 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 blah. Okay, so imagine this is a time series. Find the best fit in least square sense. We will use MATLAB routine fit and use polynomials of second, third, fourth, and fifth degrees. The syntax is t equals to fit tau OBS order. So where order should be replaced by either poly 2, poly 3, poly 4, poly 5. Okay, which call the particular fit. We run fit for T2, T3, T4, T5 to differentiate between each solution. So I'm calling for example, T2 is the best. It will estimate the coefficients for the second degree polynomial. Okay, the next step are for the second degree. After running T2, we type T2 to see if the metadata include the estimate, to see the metadata include the coefficients. The residuals can be visualized directly by the command plot T2 tau observation residuals. We can compute the residuals by doing residuals equals to t minus observation. And then we can compute the quadratic form using the P matrix as identity for simplicity. Of course, in this case, the quadratic form, we don't need to bother with the P. This is Q2, this is the quadratic form of the second degree polynomial, 1.1712. Reminder, U equals to order plus 1. And we go and repeat the same procedure for computing the quadratic form of the third, fourth, and fifth degrees. And here they are. And the quadratic form of Q2 is the smallest. Okay, so we can use these commands. Yes, the commands used in step 3 are, and here a list of the commands I use. To visualize a time series, we can plot tau OBS B. So here we have a visualization of the situation. We have the time series in blue, these blue circles. We have the polynomial fitting for degree 2, degree 3, degree 4, degree 5. So we can also compute the residuals, and here what I'm plotting is the time series of the time series and the residuals. So the observations are in blue, and the value for the residuals are in these different symbols here. So to visualize an event of prediction, now this is the interesting, the problem with prediction into the future, okay? Prediction, I told you we can be defining these values here, okay, inside the data set and outside the data set. But the prediction, when dealing polynomial, if you go outside the data set, the domain, it will run into trouble. That's what I want to show here. Okay. So if you could, you should try example number 2. Well, do example number 1 so that you can get the mechanics of this test. Do example number 2 because it's a little bit more involving, because you have to do it and there are some guidelines. You can try differently, of course. Okay. But this is a very useful test. Again, sometimes we have to fit a polynomial, and we don't know which degree we should use. Okay, and then we can basically do a test and to define, because if the consecutive polynomials start to be statistically if their quadratic forms are to become statistically equivalent. So basically, we can just stop. No, that's a criteria to decide when to stop. Now here is a comparison again. Here is I want to show problem of higher degree dealing with prediction. Okay, predictions outside the domain. For polynomial 4, this is the 4th degree, we have this decay here. For polynomial of a second order, it fits well. It's the prediction. It follows something that looks more reasonable, because that is this increase. Here, this slope, positive slope that the data does, and the polynomial of 2nd degree is following that. Yeah. So higher order polynomials, they tend to have these little bit of instability problem. Here we have now the tests. Null hypothesis, the polynomials are equivalent. Using confidence level 95%. So testing the 2nd and 3rd degree. This is the statistic that we get, and the test passes. So the null hypothesis is accepted at 95% confidence level. That means that you can use the 2nd degree polynomial fit as its equivalent to the 3rd degree fit. So we basically not need to, that would be the choice. The most reasonable choice in this case would be to use the 2nd degree.